Hi everyone, in this video we're going through section B of the 2021 MAV Maths Methods Trial Exam, number 2. So there's 2 videos prior to this that covered the multiple choice questions, and we're going to cover section B in this video. So you can use your calculator, you can use your notes, but just remember that some questions you do need to show working out. And for example, this first one, it's a show that question. So whenever you see show that, you do have to use working out. You do have to show working out. You just can't do it on your calculator. During reading time, make sure you aren't set on whether you're going to do multiple choice or the extended response questions first. I think it's probably a good idea to have a look and then decide, not go in and decide which one you're going to do first. Remember, with multiple choice, you don't lose questions if you get a question wrong. So, always make sure you answer every single one. But yeah, for these questions in section B, you obviously don't lose marks, but you can gain marks. So it's probably a good idea to attempt all that you can, but you probably will still come across questions that will stump you, and you might not be able to get full marks, but get partial marks. Okay, anyway, let's get started. So question 1A. So if 2x plus 1 divided by 2x minus 3 equals a plus b over 2x minus 3, show that a equals 1 and b equals 4. So it's a show that question. So you got to kind of say, well, let's just pretend it doesn't say show that there. Let's find the value of a and find the value of b. Now, this is the form we want this in. Okay, so I'm just going to deal with that first fraction and just transpose it till we get it into the second form. Okay, so I'm not going to let it equal it and solve it, which you can do. That's one way you can do it. But I'm just going to show you how you can rearrange this first fraction. Okay, so we've got 2x plus 1 over 2x minus 3. Now have a look at what this form that we wanted in, and we want a constant out the front. So when we want a constant, basically I need to have 2x minus 3, 2x minus 3. So when your numerator and your denominator are the same, okay, it's equal to 1. And that's what we know it's going to end up equaling. But because I have now changed the numerator, okay, because it's 2x plus 1, and now I've written 2x minus 3. What you can do is, I've got minus 3, so let's just add 3. Just so we're balancing that. Okay, so I've subtracted 3, I'm adding 3. So effectively I haven't added anything or subtracted anything because I've subtracted 3, but then I added 3. And don't forget that plus 1 on the end. Now the reason for doing that, as I said before, is if you look at, it's a whole fraction, make sure your vinculum goes all the way, but this first part, 2x minus 3 over 2x minus 3 will give you the 1. All right, let's just move on a little bit further. So we can actually separate that into being 2x minus 3 over 2x minus 3. And then I can have plus 4, because the 3 plus 1 is 4, over 2x minus 3. And then that is equal to 1 plus 4 over 2x minus 3. So a question like this is good if you had to get your answer in that form. Okay, so just make sure you're able to rearrange expressions to get them in the form you wanted. Now you could probably just solve this, but the easiest way would be just to do it how I've done it there. Okay, anyway, let's move on. Now, let f of x equal 2x plus 1 over 2x minus 3. State the equations of any asymptotes of the graph of f. Okay, so we know that our denominator cannot equal 0. So 2x minus 3 cannot equal 0. Okay, because it's undefined when your denominator is 0. So let's just solve that. So we're going to have x is equal to, bring that 3 over and divide over 2. So there's your vertical asymptote. Now, because this is a hyperbola, or hyperbolic in shape, you do need to So it might be easier if we graph it. We don't need to graph it, but let's just graph it because sometimes it's easier to just visually see what it is. Can we clear both of them? No. Go away. There we go. All right, so we've got 2x plus 1 over 2x minus 3. All right, let's just quickly graph it. Can't see it very well. Okay, so you can see you've got going to have two asymptotes. Now you can look at it on the graph if you like, but remember what we did in part 1. So we know that the graph has been shifted up 1, so you have an asymptote at y equals 1 as well. Now, if you want to look at the graph, I might just zoom. That's a bit nicer. Okay, so it's a bit hard to read asymptotes on the graph, but what you can do is go to trace and see my little cursor as we move. So as I move along, see how your values are changing. So we're going to have, let me just, should probably gone the other way. All right, so there it is. There at x equals 1.6, and then it jumps. So, I'm moving it. Sorry. Move. Come on. It's a bit, it doesn't really move. Yeah. So we're at x equals 1.4, and then it jumps to x equals 1.6. So 1.5 being our asymptote does make sense. And as we go in the y, actually, you should see that it is, go this way. Y would be approaching 1. We'll probably never get there. Okay, so see how y is approaching 1, but we'll never get there. So, I mean, you can kind of read it off your graph that way, but yeah, thinking about how the equation is written is another way of finding your asymptotes. Okay, so state the maximal domain and range of f. So your domain, all right, so that's the restriction on your x values. So it can be any real value excluding x equals 3 on 2. And your range is also any real value excluding 1. All right, so then we've got another function. So we've got a restricted domain now. We're going from -1/2 to 1/6. Explain why f of 1 of x exists. All right, so for it to exist, the range of the middle function, so they're both f of 1 in this case, has to be a subset of the domain of, and we're f of 1. Okay, so what we've got to do is say, well, what is the range, and is it a subset of the domain of f of 1 of x? Okay, so your domain is -1/2 to 1/6. All right, so we just got to do the corresponding range. All right, so we have to look at how this set domain influences our range. So on our graphing screen, we can just go to trace and then say, well, I want to know when x equals -0.5. So that's going to give me y equals 0. And then let's substitute in 1/6 and I get y equals negative 0.5. So we're in a very small part, but because 0 is the higher number, we've got to do negative a half first and then 0. So your range is going to be negative a half to 0, and that is a subset of the domain of F1. All right, so let's move on to D. So g of x equals that composite function. So it's done it for us. State the coordinates of the axial intercepts of the graph of G. All right, so I'm going to just change my function here on my calculator. We're at 1 minus 6x and 2x minus 11. And remember that f of 1 has a restricted domain, so we do need to restrict that. So I'll go back onto my keyboard. Given that, where are we going in between? Negative a half. All right, so let's sketch that. And it's very small, so let's see if we can see. Oh, I don't think I'm doing that much. All right. Okay, so there's the part of the graph that we are looking at. So you can, maybe we can zoom in a bit more. Okay, so you can see it's crossing the x-axis and it's crossing the y-axis. So all we need to do is, actually, can we do it on here? I think we could. So trace, so at 0, but it's giving me the approximate answer. So you don't want to have an approximate answer. So we're going to have to go back onto the main screen. Actually, before I'll type it again. All right, so when let's do the y-intercept first. So when x equals 0, we get the y-intercept. Okay, so 1 minus 6x, so it's just going to be 1 over negative 11. So I didn't really have to do anything complicated with that. So y-intercept, when x equals 0, we get y equals negative 1 on 11. All right, so that's your y-intercept. And then for your x-intercept, we need to let y equal 0. So we're going to use solve on the calculator. So solve 1 minus 6x over 2x minus 11 equals 0, comma x. All right, so my calculator's not in exact mode, so let's just go and change that. All right, so we've got 1/6. So 160 is your x-intercept. And I just realized I wrote intercepts there. Okay, so they're the coordinates of our axial intercepts. All right, so sketch the graph of g of x, labeling axial intercepts and endpoints with their coordinates. So we've got to go back in a sec to, actually, no, we don't have to. Let's just quickly sketch the graph. So negative 1 on 11. So if you wanted to do the approximate value, so it's nearly 0.1, so we need to go to negative 0.1. So we're down here for our x-intercept, sorry, our y-intercept, then our x-intercept is at 1/6. So just do that on the calculator. So 0.16. So just be careful with your axes. So we've got 0.1 here, 0.15. So we're going to be around here. All right, now we've got to do our endpoints. So we did our endpoints up here. All right, so actually, to make this a bit smaller. All right, so our domain, we're going from -1/2 to 1/6. So we've already got that upper point here at 1/6. So I do need to figure out what my y coordinate is when x equals -1/2. It was -1/2, wasn't it? -1/2. All right, so I'll put that into the calculator. 1 minus, actually I'll do the function. 1 minus 6 times -0.5. Let's put that in brackets. And then we've got 2 times -0.5 minus 11. And we get -1/3. So that's the other endpoint. So we're going to x equals -0.5, which is here, and then -1/3, so 0.33. We're down here, just make sure I'm drawing it correctly. It's a bit hard to put the lines on the screen. So 1, 2, about there, I think. All right, so your shape of your graph, we could go back to our graph to see it. All right, so there it is. Let's zoom in again. Okay, a very small part of the actual larger graph. All right, so I'm going to label the endpoints because it says label. We're going to label the intercepts and the endpoints. So this endpoint here is the same as our x-intercept. So that was 1, 6, 0. The y-intercept was -0, -11. Sorry, -1 on 11. And then this endpoint here was -1/2, -1/3. All right, so just make sure you do label your graphs. All right, write down a suitable integral statement that would find the area bounded by the graph of G and the lines y equals x and x equals 1/6. So the line y equals x is just a diagonal line going through the two axes. And I don't want to draw on that graph, but then we've got a vertical line going through x equals 1/6. All right, so I'm going to put on here y equals x, just so we can see where they actually intersect. So this point of intersection is going to be our lower bound. So let's find that point of intersection first. All right, so there it is. Oh, don't you hate it when it doesn't do the exact value? So we're going to have to go back to the main screen. All right, I'm going to copy this, go down. All right, so this is our function. I'm just going to replace that point, -0.5 with x. All right, so solve. There's our function g. We're going to let that equal x, so the straight line going through, and we're going to solve for x. Excuse me. All right, so we have two solutions. So we're going to, because I haven't restricted the domain, that's why we've got two solutions, because the curve actually goes back up and it's going to hit it again. But we want this first solution, the -√33/4 plus 5/4. If you're ever unsure, clearly when we looked at our graph, it was in the negative quadrant. But if you're unsure which one's negative, which one's positive, you can just change it to decimals. So let's just change that to decimals and you can see the first one. All right, then we'll go back. Okay, so when we're doing our integral, so we only have to do an integral statement. We don't have to solve it. So our lower limit is going to be -√33/4 plus 5 on 4, or you could put them all as one fraction if you like. And then our upper limit is going to be 1/6, okay, because we've got a vertical line at x equals 1/6. And then your function, which is just, where are we? G of x. And remember, it's with respect to x, so put the dx on the end. All right, I just realized I didn't, let me just clear that and I'll start again. All right, I forgot the line on the top. So if I go back to my graph, I just don't want to draw on that graph. Go back to the graph. Okay, so we do have that y equals x on top, so I'm going to have to put that first. So x, and then minus g of x dx. All right, so your top line, and then you subtract your bottom one. So x minus g of x. All right, and in part 2, we have to find the area. So I think we can do it from the graphing screen. I've never actually done it. Let's see. Okay, so yep, that's fine. Actually, maybe because we've got another line, I'm going to do it on the main screen. Okay, so definite integral, where are we? Now I can just copy that down, which is nice, and put my ones, oops, wrong place. Start again. This should go on the bottom. All right, and then 1/6 on the top. Now, I probably should have defined g of x before, but here it is here. And I just remembered I should have done x minus that. So our top line minus our bottom, and then d of x. Now, it says we've got to do it to 3 decimal places, so I'm just going to change it to decimal here, and then press enter. All right, so I get 0.030. All right, in part 3, state the area enclosed between the graph of the inverse of g and the lines y equals x and y equals 1/6, correct to 3 decimal places. All right, so with the inverse, if I just go back onto our graph to see the graph again, when you do an inverse, it gets reflected along the line y equals x. So this blue line is going to be reflected. So the part that is underneath it is now going to be above it, but it's going to be symmetrical. So your answer to part 3 is the same as part 2. So it's just 0.030 because I can't draw on my calculator, but that blue line gets reflected. And so that area between the red line and the blue line is the same, whether that blue line was above or below. Okay, so what I might do is show you the solution to show you that. Okay, so you can see part 3 there, the area. All right, let's move on to the next question. The graph of dt equals, and that's pretty hard to read, e to the negative kt sine kt can be used to describe drug absorption in the bloodstream, where d is in milligrams per litre and time t is in minutes, where t is greater than or equal to 0 and k is a positive real constant. So we've got to find the derivative. It is only worth 1 mark, so we can do it on our calculator. Go to our main screen and we can just go to calculation and we want to find the derivative. All right, so we've got e to the negative k. Now just make sure you put a multiply between your k and your t. Otherwise it'll probably read it as one variable, times sine, I might do times sine of kt, so k times t, and variable is t, so I need to change that to t, and we're only doing one single derivative. So looking at degrees, I need to put it in radian. Oh, how annoying, I can't change it into radian. So actually, I don't think it matters when we're taking the derivative anyway. Or maybe it does. Actually, let's go back up and change it to, there we go. All right, so it's given me the answer in degrees. So I'm going to change it from degrees into radians. There we go. So I did have to change it into radians. So we've got the derivative is equal to k cos kt minus k sine kt e to the negative kt. All right, so part B, hence show that the general solution for the t-ordinates of the stationary points in the graph of dt are found by solving tan kt equals 1. All right, so what we have here is, so I need to use, hence show the general solution to yours. So we're looking at stationary points. So remember, when we're doing stationary points, your derivative is equal to 0. So that means k cos kt minus k sine, and I just realized there should have been brackets around all this. So all around this, whoops, not that last one because I haven't finished, sine kt, and then we've got e to the negative kt. All right, so just be careful not to forget your brackets because that would have been completely wrong. All right, so what that actually means is we can think of the concept of the null factor law. So when we've got two numbers multiplied by each other and it's equal to 0, that means a can be 0 because anything multiplied by 0 is 0, or b can equal 0. So in this case, even though it's a little bit more complicated, we can say all right, let's take this first bracket, so k cos kt minus k sine kt is equal to 0, or e to the negative kt equals 0. Now we know that this cannot equal 0, okay, because you can't have any power and get 0, so that can't equal 0. So we're just going to focus on this part here. Now remember, tan is equal to sine over cos. So that's, we've got to just manipulate this a little bit until we get this answer here. All right, so what I'm going to do is take k as, oh, let me just think. All right, another thing I should have realized is k is a positive real constant. So we can actually just get rid of k as well. And we're just left with that multiplier k minus sine kt equals 0, because k also cannot equal 0. All right, so let's just put a lot of working out here. All right, so I'm going to take that sine over to that side. Now at this point, I've got cos kt equals sine kt. Remember, I want to get this sine over cos, and the 1 can also come from having your numerator and your denominator the same. So if I divide now both sides by cos kt, okay, so it doesn't matter that I'm doing that. I'm not actually changing anything because I'm doing the same thing to the left-hand side and the right-hand side. So therefore, sine kt over cos kt is tan kt. And now we've got cos over cos, which is 1, which is what we have to do. All right, state the general solution for the equation dt equals 0. Give your answer in terms of k. All right, so on your calculator, we just need to go to solve, and we're going to do 10. Let's make sure you do k times t, and we're going to let that equal 1, and we're solving for t. Okay, so this is our general solution. So hopefully you're now familiar with general solutions. How you need to interpret this is this CONSTN just means the constant n. So when I'm writing my solution, we've got t equals pi times some constant, which is just, we can call it any letter you like, but let's just stick with n. So pi n over k plus pi on 4k. Now, that's what you read off your calculator. You can't write the const n. You do need to replace it with an n. But the last thing you need to do is say where n is an element of z. So z being an integer. All right, so when you're doing any general solution, you need to not only give the solution, but write at the end where n is an element of z. So where n can be any integer. All right, so I did just check the answer, and we do have restrictions on t, which I probably should have realized. So t has to be greater than or equal to 0. So with our solution, we can't have n is an element of z. All right, so n has to be an element of 0 and actually that's not, or n can be any positive integer. I should probably put curved brackets around that. Now, if that notation is too difficult, you can say where n is greater than or equal to 0. Oh, actually, no, that's not true because it has to be an integer. Don't use that last notation. No, we do need to use this notation because it can only be an integer. It can't be, so an integer is a whole number. So n is an element of 0 and, or n is an element of any positive integer. And if we're looking at k, all right, just defining k, even though it was defined before, and I don't think you would have to do it here, but it does have it in the solution. So k is a positive real constant, so k is also an element of any real positive number. Okay, but I don't think we have to put that in, but it's in the solution, so we'll just put that in as well. All right, if that notation's a bit messy, isn't it? So there it is, it's a little bit easier. N is an element of 0 and, or positive integers. Okay, part 3, hence find the t ordinate in terms of k of the maximum stationary point of the graph of, okay, so we've got dt, and we're going, our domain is from 0 to 2k, to 1k. All right, so we're going to use the general solution from part 2. So t equals pi n on k plus pi on 4k. All right, so let's let n equal 0. So when n equals 0, we're going to have t equals pi times 0 on k, so that's just 0, so it's going to be pi on 4k. And we can actually substitute in other values of n, so we can go on and do n equals 1, which is the next integer. So then we're going to have t equals pi on k plus pi on 4k. And if I just bring them together to be the same denominator, we're going to have 4 pi, so 5 pi on 4k. All right, so I could keep substituting in values of n, but we're not going to be inside our domain. So this is not inside the domain of 0 to 2 on k. So the only possible solution we can have is t equals pi on 4k when n equals 0. So there's our T ordinate there. All right, let's move on to the next one. Juniper is in hospital and needs a particular drug for her pain. Let D, we've got a restricted domain, okay, where the particular drug in Juniper's bloodstream is measured in milligrams per litre at time t minutes. After how many minutes will Jupiter's bloodstream contain the maximum amount of the drug? State the maximum amount of the drug. All right. This question is worth 2 marks, so we've got to kind of think about, well, what are those 2 marks going to be? So after how many minutes would contain the maximum amount of the drug, and state. So we've got to do how many minutes and the amount of the drug. Now we can do that on the calculator. All right, just go to interactive calculation, and what do we want? The maximum. Okay, so our expression is, now I probably should define this. We're going to use it later on. I'm just going to write it. Actually, you know what? I'm going to define it because I haven't defined for a while. All right, so I'm going to define it. I'm just going to use F. Probably should use D, but actually, and I'm going to use T. Equals 10 times E to the negative 0.2 T times sine of 0.2 T. Make sure I've written that down correctly. 10e to the negative 0.2 T. Awesome. Okay, so let's go back up here. Calculation, maximum. All right, so we want f of t, and the variable is t. All right, and we're going from 0 to 10, so it's important to do that because we might get a lot of solutions. All right, so your maximum value is 5 root 2 e to the power of negative pi on 4, and then there's our value of t. Now, it might seem a little bit weird to give time in terms of pi, but it hasn't asked for you to round it, so we're just going to leave it in terms of pi. So t equals 5 pi on 4, and the maximum is equal to 5 root 2 e to the power of negative pi on 4. Now, if you needed to show a bit of working, you can say, all right, let's let dj, the derivative, equals 0. Okay, so that's what you would do because it's a stationary point, but we can just do that on the calculator. All right, find the average rate of change of the amount of the drug in Juniper's bloodstream in milligrams per litre per minute over the interval 0 to 10. Give your answer correct to 3 decimal places. So we need a approximate answer. Average rate of change. Okay, so we're going to do just the gradient between these 2 points. So we need to substitute in 0 and 10. All right, so our function 10 minus, actually, did I do that around the right way? Okay, and then 10 minus 0. It is worth 2 marks. I don't know why. It's not a very hard question. But on the calculator, we can just do in our fraction. So f of 10 minus f of 0. And then 10 minus 0 is just 10. And we do have to do it in decimals, so I'm just going to change that to decimals. All right, so 3 decimal places, so 0.123. So it's worth 2 marks, so you do need to show that substitution that I just did. You can leave it in terms of D, that's fine. All right, show that the graphs of DJ and P intersect at only one point and that it is not at the stationary point found in part C. Okay, so it's worth 2 marks. So if they intersect, they're equal to each other. So let's just do dj of t is equal to p of t. Now, because it's a show that question, we should really show a bit of working out. So I'm going to write dt, so 10e negative 0.2t sine 0.2t and pt 10e negative 0.2t. All right, so if I wanted to get rid of this, I can divide both sides by that, so that cancels, and then when we divide by this, it's going to equal 1. And then we can just solve for t. So 0.2t equals inverse sine of 1. So t is equal to now we're only going from 0 to 10. So on my calculator, I'm going to do that. So inverse sine 1. Is that? Oh, pi. Divided by 0.2. 5 pi on 2. All right, so, I mean, that's the point. And that is not the stationary point found in part C. I'm not sure how he's to do that because the stationary point was at t equals 5 pi on 4, which does not equal 5 pi on 2. All right, let's move on. Find the difference in time between the maximum stationary point of the graph and the point where the graph of y equals e to the negative kt is tangential to d for k equals 0.2 and k equals 0.02. All right, so let's first look at k equals 0.2. So our domain is going to be 0 over 2 divided by 0.2, which is just 10. And dt is going to equal e to the negative 0.2t sine 0.2t. All right, so let's have a look first of all. Find the difference in time between the maximum stationary point on the graph. Okay, so we'll find the maximum point first. So the max at, all right, so we'll do that on the calculator. Maximum. Okay, so we've got e to the negative 0.2t times sine 0.2t and t, and we're only going from 0 to 10. All right, so that's at t equals 5 pi on 4. And we want to find the tangent. All right, so for the second part, I've just let the two equations equal each other, but just make sure you restrict your domain as well for t. Okay, so similar to what we did in part E. So we're going to get now t equals 5 pi on 2. So if we're looking at the difference in time between the two of them, we just need to take the higher value, which is 5 pi on 2, and subtract the smaller value, so 5 pi on 4. So the difference in time for k equals 0.2 is 5 pi on 2. And k equals 0.2. So I might just have that there because we're going to have a little bit of working out for the next one. All right, so part 2. All right, so when k equals 0.02, our domain is going to be from 0, then 2 on 0.02 is going to be 100. Okay, and then we just pretty much do the same thing. So I'm going to just scroll up and change this to 0.02 and this to 0.02. All right, and I get t equals 10. And then I'm going to change this one here to 0.2 and this one to 0.2 and then this one to 0.2. And I do need to change my domain to 1 to 100 and we get 25 pi. All right, so the difference between the two of them, let's just leave it in exact form. So it's going to be when, so 25 pi minus 10 when k equals 0.02. So there's our second answer. Right, I just realized in my working I didn't change this domain. So it's not 10, it's 25 pi on 2. 25 pi on 2, so this should be 25 pi on 2. So 25 pi minus 25 pi on 2 is 25 pi on 2. All right, so moving on to part G, find the difference in time between the maximum stationary point on the graph and the point where the graph is tangential. Okay, so we're giving our answer in terms of k. So we can kind of see the relationship, what has happened in the previous question, and apply that knowledge to question G. All right, so sorry, I had to really think about this question, very tricky. So we're going to find the derivative first. Okay, so we're going to let the derivative equal 0. So I've done that on the calculator. So what I did, I might just go back, I defined the function. So I didn't use D, I used F, just because it was on the keyboard, but you can use D. So I defined the function, and then I found the derivative of the function, and then I solved, let the derivative equal 0 and solved. Okay, and I restricted the domain, but because we're in terms of k, it's giving me a few solutions in terms of k. So we've got to think, well, what could it possibly be? So we know t has to be greater than 0. So if I'm just substituting in different values of n, so remember n with our solutions, we get, so any integer we substitute in for n. So if we're going to have n equals 0, the first solution is going to be negative pi on 2k. Okay, so t has to be between 0 and 2 on k, so it can't be that one because it can't be negative. All right, the next one we've got 2 pi on k. Now I need to write that down. 2 pi. No, sorry, that's just going to be 0. So 2 pi times 0 on k is 0 plus pi on 2k. So put pi on 2k. And the next one, we're going to have pi on 4k. And then we've got 5 pi on 4k. So from our solutions, so I restricted the domain. All right, I might actually write down that first one. So negative pi on 2k. All right, so sorry, I'm really struggling to answer this the best way possible, but I thought let's think of k just as 1. Okay, so in the previous question we had k equals 0.2 and k equals 0.02. But let's just look at a basic graph, not a basic graph, but let's just look at letting k equals 1. So we've got e to the negative x, so we can't put in t in here, so it's just going to be negative x times sine of x. So graphing that looks something like that. And we're only going from 0 to whatever value. And you can see we've got a maximum here. All right, so we want to go in the positive. We've got to be above 0. So that point there, we can just go to, all right, let's solve maximum and just keep moving until we get to that point, and you can see it's there at 0.785. Now, if I change the value of K, so to maybe let's do 2. And it's pouring with rain. Right, so oops, I want to go back. Okay, so you can see it's changed now. You can hardly see that maximum value, but it looks like it's halved it, okay, what it was before. So if I go back to my main screen, remember how we had all these different solutions? The one that matches up with the one that we see is pi on 4k, okay, because I did pi on 4 and I get the same answer as this one here. So what we're going to have is t equals pi on 4k as our maximum stationary point, and then we want to look at the point where they cross. All right, so for the second part, looking at where they intersect, okay, so dt and y. If we go back up here, remember when I was solving it by hand, we ended up with 0.2t equals inverse sine of 1. So I'm going to use that knowledge to just do this here. So we're going to have kt equals inverse sine of 1, which is, if you know your exact value, is pi on 2. Now you can also do that on your calculator if you like. All right, so dividing both sides by k or multiplying by 1 on k. So that cancels out, so t is equal to pi on 2k. All right, so there's our 2 points of t. Now, if we're looking at the difference in time, so we've got pi on 4k and pi on 2k. All right, so we take the larger of the two, pi on 2k, subtracting pi on 4k, and we're left with pi on 2k. Sorry, not pi on 4k, sorry. Probably should have done it on the calculator. All right, and nearly at the end. All right, I might actually leave this video here because it's getting close to dinner time. It's probably going to take me, I just realized there's 2 more questions, so 3 and 4 I need to still do. So I might do them in a separate video, all right, because we're already at 53 minutes, so I don't want to go too long. All right, bye girls.